Hello, everyone. Okay, so let's move on to part two of chapter 9, where we're talking more about about Lewis structures. So, um, we talked about drawing Lewis structures, and sometimes, we showed in the case of formaldehyde that there's usually more ways to write a structure, one Lewis structure. There's more than one way to write the structure. And when we have that situation, we come across what we call resonance structures, where they are two. There's at least two or more equivalent or valid Lewis structures, and a good example of that is this compound here, sulfur dioxide. Okay, so here let's just put in the charges, just so we know that they don't have the same formal charge based on how many electrons are around them. So oxygen here will be 0. You could just put a 0 here. But you see that 0, that double bond is different from the single bond over there. So it actually has a different charge. And I already wrote it wrong. So it should be -1. Then the sulfur here must have a positive charge because sulfur dioxide is neutral. And then you see right here, we can move these electrons to form a new double bond and push these electrons out here. So the lone pair now, there's an additional lone pair on the oxygen on the left. And when that happens, the charge here switch places. So when we rearrange the electrons from lone pairs and double bonds, that's called a resonance structure. So in this case, sulfur dioxide can be represented by two different resonance structures. Okay. So we may ask ourselves, okay, if we do that, which one's the true structure? Which one's correct? Well, the short answer is that none of them are absolutely correct. What actually happens is that the actual structure is a mixture of both of these structures. Okay? So the two Lewis structures, they kind of give us this idea that one of the sulfur-oxygen bond lengths is shorter than the other because they're alternating between double and single bonds in one structure, right? And then if we look at the other structure, they're switching places, right? However, if we just said that the structure is only one of these two Lewis structures, if we said the actual structure is only one of these, we would expect a one SO bond to be longer than the other, right? But in actuality, in experiments, it's shown that these two sulfur-oxygen single bonds have identical lengths. So this can't be explained by just looking at one structure, right? Because one of them has a single bond and one of them has a double bond. So we say the actual bond is intermediate or in between that of a single SO bond and a double S double bonded O bond. Okay? So what causes this? Well, what causes this is that if we can write an equivalent structure, that is called a resonance hybrid. So the best description of this is a hybrid. For example, yourself is a hybrid, maybe a hybrid of your parents. So we can't explain how we look based off the appearance of one of our parents. It's usually a combination of both. So we call it a hybrid, just like for chemistry. If we can't describe a molecule with only one Lewis structure, we must describe it as a hybrid of all possible valid Lewis structures. Okay? So what I like to do is, I think of it kind of like music. So if we have notes in the chord, they often resonate right when you strike two notes in a single chord. More simply is that they mix to give something that is more than just the addition of their parts, right? So it's kind of like the same thing in chemistry. the two Lewis structures for the sulfur dioxide, they're kind of in resonance, so they kind of resonate as one instead of being, you know, one or the other, just like the music example. Okay, so to kind of represent this hybrid here, we use double-headed arrows. So double-headed arrows meaning we have an arrow, but there's an arrow on both ends. Okay, so that means they're resonance structures, just like how I've drawn up here. So that indicates a resonance structure. Okay. All right. Okay. So more importantly, the resonance hybrid is the true picture of the Lewis structure for such molecules. Okay, and we'll have more time to do more examples. Okay. So one thing to keep in mind is that they are not isomers. So isomers are when two structures have the same chemical formula, but the bonding between atoms, there's different connectivity, right? So they do have the same formula, but they don't have the different arrangement of the atoms, right? If we look at the arrangement of the atoms, they are the same. What's different is the electron distribution around the molecule. So those are called resonance structures. They are not isomers. So different arrangement of the electrons, and you know that can lead to different arrangements of double and single bonds around the atoms, but generally speaking, the positions of the atoms are at the same coordinates in both structures. Okay. All right. So let's move on to this exercise where we'll demonstrate now how to draw resin structures here. All right, so acetic acid is an acidic compound. It dissociates to some extent in water to give you acetate ion, CH3, COO-. So we're going to write the structure for acetate ion. Okay, so we have two carbon atoms. So the best way to draw this is to first draw a skeleton here based on the formula. So we have a CH3 group, okay? And then right next to it is COO-. So the best thing to do is write C, and then instead of putting the oxygens together, it might be better to have the both oxygens bonded to the carbon atom, so they are not, so carbon can have an octet, okay? And then we'll put the negative charge later. All right, so if we look here, we have two carbon atoms. So that's going to give us 2 times 4 electrons, okay? Gives us 8 electrons, okay? We have 3 hydrogens, so 3 hydrogens, that's going to be 3 times 1 electron equals 3 electrons. And lastly, we have 2 oxygens, so 2 oxygen atoms. We have 2 times 6 electrons, that gives us a total of 12 electrons. So if we add these all up, we get 12 plus 8, 20, 23 electrons. Oh, but we forgot something here. We have to add the negative charge plus the negative charge. That's 1 electron. Gives us a total of 24 electrons. Okay, there we go. So let's put first single bonds between the elements. CH, CH, CC, CO, and CO. Okay. So right now we have 12 electrons, right? 2, 4, 6, 8, 10, 12. Now let's put the remaining electrons as lone pairs. Okay. So we need 12 electrons here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so now we have an octet, and we have 24 electrons around the whole molecule. However, carbon, it doesn't have an octet, right? So let's move one of these lone pairs into a double bond, okay? So we're going to take that lone pair, make it a double bond. Okay, so now the oxygen atom and the carbon atom have an octet because we decided to share one of the non-bonding pairs of electrons on oxygen between oxygen and carbon. So that helps satisfy the octet rule for both of these molecules. Okay, so we know the negative charge is somewhere, and we know it can't be on the C double bond O. That's because if we look around oxygen, it has 6 valence electrons around it. And then if we subtract that number from its normal group number, that gives us 0. So oxygen here is 0 here. So the negative charge must be around this oxygen that has a single bond. Okay. So you notice that we have 2 oxygen atoms, and we can also think about putting a negative charge on the other oxygen atom. So we can actually move electrons here, and this gives us a place to draw another resonance structure. So what we have here is the same framework of atoms around for the skeleton, but what happens here is that the oxygen atom can shift between a negative charge and a neutral charge, like so. Okay, so both these structures are valid resonance structures, and they're actually equivalent, but you see here the negative charge can shift between one oxygen atom and the other, so they are equivalent. Okay. So let's answer this next question. Why don't the 2 structures of the acetate ion so why don't these 2 structures let's just modify this. Why don't the 2 structures of the acetate ion, okay, let's cross this out. I think I meant to put a picture here, but I forgot. No matter. So here are the 2 structures of the acetate ion, right? Why don't they represent a pair of isomers? Well, like we said before, they have the same basic structure. Meaning they have the same basic connectivity of the skeleton, right? Structure / connectivity of atoms. So they are not isomers, okay? Isomers would be if, like, say, okay, my oxygen, what would be an isomer? So an isomer of acetate would be something like, God, this is hard. I don't know. What would be an isomer of acetate ion? Something like this, I suppose. Okay, say we have something like this. Okay, so this molecule does not exist in in the slightest definition of the word. This does not exist. And sorry, I'm going to OChem mode. Sorry about that. So this molecule doesn't exist, but this is what it would look like. Okay. Okay. So we see here, this is CH. So there's 2 carbon atoms, 3 hydrogens, 2 oxygens, right? But look at where the negative charge is. It's switched places, and the extra lone pair is on carbon now, which gives it a negative charge. But don't worry too much if you don't see why it's -1. We'll talk about that later. But you see here, the one of the hydrogens is now connected to the oxygen atom. So the location of the hydrogen atom is now different, and this will be an isomer of the acetate ion. Now, this probably will never ever form, and that's because carbon does not like to have negative charges, and that's because it's less electronegative than oxygen, so it can't stabilize or hold on to a negative charge and be stable like acetate is. And that's why we see acetate in the form we drew above and not in this form. This wouldn't actually be called acetate. You will call it something different. We call it a carbon anion, and it's not predicted to exist. So, but in theory, in terms of structures, this would be an isomer, but acetate ion, not isomers. Okay. Alrighty, let's move to the next question here, or next topic here. All right. So let's do this exercise. The molecule N2O, which is a product of oxidation of fuels. When you drive your car, right? You intake the fuel, you ignite it in air. It has oxygen and nitrogen in it, and then eventually you get some oxidation products, the nitrogen oxides. And they some are good for us. They're generally not good, and that's because they interact with ozone and the air and the upper atmosphere. But it's a good exercise to think about. Okay, which one of these structures is acceptable for this molecule? And I think it's particularly helpful to evaluate resonance structures. Okay. So, right, okay, so which structures are acceptable, which ones are not? Let's explain why. All right. Okay, so let's calculate first the number of valence electrons for N2O. Okay. So nitrogen oxide, dinitrogen oxide, or dinitrogen monoxide, okay? So we have 2 nitrogen atoms. So for nitrogen, we have 2 times 5 electrons each equals 10 electrons. And then for oxygen, we have 6 electrons for the solo oxygen atom, okay? So if we sum the total up here, we get 16 electrons. Okay, so which ones are valid? Which ones have 16 electrons? So let's look at A here. So A, we have 2, 4, 6, 8, 10, 12, 14, 16. So this is 16 electrons, right? So that's okay. But what's the problem here is that for letter A, so A, the central nitrogen atom does not have an octet. So it's not particularly stable. So not very acceptable here. All right, let's look at letter B. B, okay. We have 2, 4, 6, 8 electrons around the nitrogen oxygen bond. Then we have 10, 2, 4, 6, 8, 10, 12, 14, 16. So 16 total electrons. However, the central nitrogen has no octet again. So that's not acceptable. So no octet on central nitrogen atom. All right, let's look at C. So C, we have 2, 4, 6, 8, 10, 12, 14, 16 electrons in the molecule, and all the atoms have octets now, so that makes this molecule acceptable. So let's circle the acceptable ones. So this one's good. A is no good. B is no good. C is okay. C is pretty good. Okay. How about letter D? Okay, we see we have a triple bond between the nitrogens. That maintains the octet for them. And then we have also an octet on the oxygen. So this is good as well. And we see here we have a total of 16 electrons. So D is perfectly good as well. Okay. E. Okay. So E, now let's put the double bond between the other two nitrogens. Now, when we do that, we do get 16 electrons for the molecule. However, there's still no octet on the nitrogen atoms. So, again, just by switching those two bonds, or switching the bonds from oxygen, so if we look at B, right? So B basically goes to E as a resin structure if we do this. Make a double bond here, push a double bond out, make it a lone pair, and we get structure E. So there's no change in anything really, because now nitrogen still doesn't have an octet, because you push electrons to form a double bond, then you push electrons out again, so you have a net result of zero change. So here we have no octet on central nitrogen. So we want to make sure that at least all atoms have an octet, okay? So we shouldn't have to expand or limit an octet. We always want to aim for at least all atoms having an octet, except for hydrogen and some exceptions, like boron, okay? All right, let's look at F. So F here, let's see here. So the central nitrogen now has one too many electrons, and since it's not sulfur or a third row element in the periodic table, it can't have an expanded octet. So here we can say for letter F, so we can say central nitrogen has too many electrons around it. Okay? And also oxygen in this case has no octet. So you can't even call this a resin structure because it's not valid, because nitrogen has more than an octet around it. So F is no good either. Okay. Not acceptable. G now. All right, let's look at G. So G looks pretty good actually, right? Everything has an octet. Nitrogen, octet, oxygen as well. But let's count the electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. So this one is not good because it doesn't have the total electrons that the formula states it should have. So we say too many valence electrons. So too many valence electrons here. So that is not a good structure. Okay? And lastly, H, and we go over here. Okay, so H, so what did we do for H? Okay. So H, so let's see here. Are they related by resonance? Maybe. So if we look between C and D, we can see the relationship here is that this lone pair, okay, donate its electrons here and push these electrons onto the oxygen, and that's how we get the triple bond on the bottom for letter D and the single bond right there. Okay, now if we think about H, right, how do we get to H? Well, we can think about it like this. Say we did this. Okay, here's a different resonance structure now. So let's erase these arrows I just drawn, just so we can write this new resonance structure. Okay, so to get from C to H, instead of drawing it that way, we draw the electrons from the oxygen right here. And then we draw a lone pair forming on the nitrogen on the left, and we get the structure H. So that's a valid resonance structure. So H is valid as well. So the three best structures for this molecule is actually C, D, and H. So then if we count the electrons for H, we see we have 2, 4, 6, 8, 10, 12, 14, 16 electrons. So these are the best three valid resonance structures for N2O. Okay. So I know that was a lot, but it kind of gives us practice writing the Lewis structures and evaluating which ones are valid, and getting you comfortable, getting students, in the right frame of mind to think about Lewis structures and think about how the distribution of valence electrons affects the stability of these structures. Okay, so let's end the video here, and we'll pick up in the next video. So see everyone then.